Alright, this video is going to be on how to find limits at infinity. And when you find limits at infinity, you're going to be dealing with rational functions, as we have in a lot of the cases of limits. And we're specifically going to be looking at rational functions where we have horizontal asymptotes, because that's actually where we start to say as x is approaching negative infinity or x is approaching positive infinity. In the past, you might have heard horizontal asymptotes being described as end behavior asymptotes, and that's because of this relationship we have with limits. So I want to give you guys a couple examples just to remind you guys of maybe what you've learned in the past. So if we remember cases where we might have a problem like f of x equals like 3x to the second plus 1 over 5x to the third plus 2x, something like that. When we dealt with these in pre-calculus and we were saying whether or not there was a horizontal asymptote, we would say here that they had a horizontal asymptote at the line y equals 0. And the reason that we knew that was because the degree of the numerator, the highest exponent there, and the degree of the denominator, so the highest exponent there, we noticed that the numerator was smaller than the denominator. All right, so here we're going to say that the degree of the numerator was less than the degree of the denominator. And when that was the case, we had a horizontal asymptote at y equals 0. So now, when we start talking about end behavior asymptotes, then we're going to say the limit as x approaches positive or negative infinity, so as the curve follows the asymptotes out forever to the left and to the right of that function, they're going to follow that horizontal asymptote. And so that means that the limits, as we go forever, the y value that we would be approaching would be 0. So you'll notice that the horizontal asymptote kind of predicts the limit. We have some similar information there. So that's the first case. The second case is if we had like f of x equals, let's say, 3x squared plus 1 again, and this time we have negative 6x squared plus x minus 2, something like that. So here we have a situation where the numerator, the degree of the numerator equals the degree of the denominator. And what happens here is if you look at these, we would look at the coefficients, and we would say that the horizontal asymptote here was y equals, and we would divide those numbers, and we would say it equals 1/2. All right? So the way that we would describe this here is we would say the limit as x goes to positive or negative infinity of f of x, when you have those two degrees equaling each other, is it's just going to equal whatever those coefficients happen to be. So I'm going to say coefficient of the leading degree, or the highest exponent there, and then the coefficient of the denominator. So numerator divided by denominator. And that's because, same reasoning, we have horizontal asymptote, it just happens to be at a number other than 0. So as we follow the graph to the left forever and to the right forever, we're just going to be getting closer and closer and closer to that horizontal asymptote. And then our last situation might be something like f of x equals maybe 3x squared plus 1, you can tell I'm being lazy, divided by x plus 5. And here, if you guys recall, we would say there isn't a horizontal asymptote at all. We would say there's a slant asymptote or an oblique asymptote. And if you guys recall, these asymptotes were in the form y equals mx plus b. These were slanted lines. And so that means that as the curve is following that line, that curve is not going to go horizontally and be approaching one y value and just getting closer and closer to it. That curve is actually going to be shooting up forever or down forever. It's going to be going off to infinity. And so that means that when we look at these ones, where we have the degree of the numerator is bigger than the degree of the denominator, then the limit as x goes to positive or negative infinity of the function is also going to be positive or negative infinity. And we know that whenever we see that, we actually say that does not exist, it is unbound. because positive infinity and negative infinity are not numbers that you can actually equal. Okay? Now, we dealt with things in this simple of a manner. We didn't go much deeper into it than that. And today we're actually going to go a little bit deeper than that. And so I want to think about some numbers and the logistics of plugging in an infinity for a number. And you guys know that it doesn't make a lot of sense to plug in infinity. But for this assignment, for us to practice this, we kind of have to think about it. So, if I was to think about plugging infinity in for x squared, so I'm going to write this better. I'm going to say maybe f of x is x squared, and I want to go ahead and plug in infinity. Then that means I'm doing infinity times infinity, and that's just going to kind of be infinity. It's just a large number. All right? For the same thing, if I want to think about plugging in negative infinity, then that gives me negative infinity times negative infinity, and that now is positive infinity. So if you guys can think about that, a negative number times a negative number equals a positive number. That's kind of something to keep in mind. All right? And we can even think of this as like our final answer is like infinity squared. We took a large number and multiplied it by itself, and we got an even larger number out of it. That's kind of a good way to think about it. So when we talk about this problem up here of we have 3 times x squared and negative 6 times x squared, this infinity squared and that infinity squared are the same size, which is why we can kind of think of them not being there. And then we can think of, oh, that fraction, 3 over negative 6, that kind of makes sense. If we look at this problem at the top, let's think about what we have if I did f of x equals x to the third instead, and now I want to plug in, I'll still plug in positive infinity. Now that means infinity times infinity times infinity, right? And that's going to be a large number. But if you think about comparing these, this one right here where I just did infinity times itself twice, and this number here where I did infinity times itself 3 times, I end up having a large number divided by a much larger number, all right? So it's kind of like saying I have a large number divided by like a large number, all right? And because of the way fractions work, the bigger the discrepancy between these two numbers, like 1/5 versus 1/79th versus 1/500th, the bigger the discrepancy between those numbers, the closer that fraction is to 0. And so that's why when we talk about this case right here, we're going to say that because we have an x squared and an x to the third, and we're plugging infinity in for those numbers, we're going to say that's a huge discrepancy, and that's why we say we have a horizontal asymptote of 0. All right? Now, the opposite of this is true if I were to switch these and say that I had the higher exponent on top and the lower exponent on the bottom. Then if you think about how fractions work, if I have 3 over 2 compared with 500 over 2 compared with 10 million over 2, you'll notice that the larger the discrepancy there, the bigger the number happens to get. And that's what's happening in this third case is the discrepancy between these with an x squared and an x, infinity squared is going to be much, much, much larger than just infinity. And so that's why we say if we have a huge number divided by a number that's smaller than it, overall we're going to expect that number to get larger and larger and larger, and that's why this is going to approach infinity. So I know that that's kind of a weird concept, but we're just going to think of infinities as large numbers, and we're going to think like what large number wins. So in this case, anytime the larger number on the bottom wins, then you get 0. If the larger numbers, if they're the same on the top and the bottom, then you just look at the coefficients. If the larger number is on the top and that's what wins, then you're going to overall say infinity. So those are the 3 cases, and hopefully I've done a reasonably good job explaining it. Now the part that's kind of interesting on this one is if I think about plugging negative infinity in on this one, we would say negative infinity times negative infinity times negative infinity actually equals the negative version of a huge number. So it's possible for us to maybe evaluate these and say, oh, that number, whatever I get for that answer should become negative. I've got to be careful to watch for that. All right? Now, we are going to have another one that's kind of tricky. We're going to say f of x, and we're going to say the square root of x squared. So on this one, if I was to evaluate this for positive infinity, then because of that square root symbol, I know that I'm going to have the square root of positive infinity times positive infinity, and I know that my answer is still going to be positive, right? And if I evaluate it at negative infinity, I'm still talking about this whole squared thing, so I've got negative infinity times negative infinity. I'm still going to have a positive infinity there because I multiplied a negative number times a negative. But the interesting thing about these problems is when we talk about the degree of something like this, I'm going to think of that square root sign and that squared sign canceling out. And so I'm going to think of this for degree purposes as being x to the first power, and this having a degree of 1. All right? Even if I change the function to have a +1 on the end, and it's technically not proper for me to take the square root of x squared, even then, I'm going to say that this is a degree of x to the 1, and that's what I'm going to consider when I look at these pieces right here. Okay? And I understand that's going to mess with your brain a little bit, so I'll answer as many questions in class as I can. So just to kind of recoup that, let's say we were talking about f of x, and our function was like the square root of 2x to the 4th plus 7. Then here, for the purposes of the degree of this expression, I would say the degree of this expression is the square root of x to the 4th would be x squared. So this would have a degree of 2 for the purposes of my problems. Okay? So it's okay if that messes with your brain a little bit. We're going to do some problems now, and hopefully you guys will be okay. All right. So we are going to use limits to show the different asymptotes. So our first example, using limits to show asymptotes. The first example is going to be the limit as x approaches 3/2 of the function x squared minus 1 divided by 2x squared minus x minus 3. So there's our function right there. And already I'm assuming I'm looking for a vertical asymptote, because if it was a horizontal asymptote, they would have said as x goes to negative infinity or positive infinity. And so I am going to remember from the other day when we were trying to find limits algebraically or trying to do it by hand, to do this problem, if I knew that I couldn't plug in 3/2 in the bottom, and here if I tried that I would get 0. So I know I can't just plug it straight in. I know I can't do that. So the other method I probably would have done is I would have factored this. I would have factored the top using difference of squares. And I would have factored the bottom probably using slide divide, but whichever method you're comfortable with is fine. And when you factor these, this is what you would have gotten. So what you would notice is that, yeah, there's a hole in this function, but it's not at the point we're trying to plug in. The point we're trying to plug in is 3/2, and that's not part of the hole. And if it's not the hole, it means it has to have been the vertical asymptote. So I'm going to say that this limit does not exist. It must be unbound because of what I know about how these functions work. And so I'm going to conclude that there is a vertical asymptote at the line x equals 3/2. All right. Now, for me to find the horizontal asymptotes, because there could be more than one, that's why I said it plural, I'm going to find the limit as x goes to negative infinity and as x goes to positive infinity. Because it's possible that one side of the graph is following one asymptote and the other side of the graph is following another asymptote. So I'm going to go ahead and do both of these. And x squared minus 1 x minus 3. Now, if we plug negative infinity in for the x squared, that is so much bigger than negative 1 that the negative 1 essentially doesn't mean anything for the problem. And if I plug negative infinity in for this x squared down here, that is so big that this negative x and negative 3 are not going to mean much. So when I do this problem, I'm just going to focus on the degree. I'm going to focus on that leading power there, which is why we do these problems the way that we do them. And I'm going to do it the same on this other one when I plug in positive infinity. Right? So one of the things we're going to pay attention to when we do these problems is when I plug in this negative infinity, am I going to keep the sign of the original problem, or am I somehow going to have a negative in my answer now? And the answer is I'm going to keep the same sign, right? Because negative squared is positive and negative squared is positive, and so there's a positive divided by a positive is going to stay as a positive answer. So here I have infinity squared, and those are the same size. So they're essentially going to cancel out, and I'm going to be left over with this coefficient, which is a 1. I'm going to be left over with 1 divided by 2. So based off that, I know that on the left side, there's a horizontal asymptote I'm approaching on the left side, and that horizontal asymptote is at y equals 1/2. And then I'm going to do the same thing here. I'm going to plug in positive infinity. And you'll notice that when I plug in positive infinity squared, these are exactly the same size. And so I'm going to ignore those, and I'm just going to look at the coefficients. And again, I get 1/2. And so the horizontal asymptote is 1/2. Overall, there's just one of them, it appears. And that's y equals 1/2. So we found our vertical asymptote, and we found our horizontal asymptote. All right. Same instructions, use limits to show the asymptotes. But this is going to be with one that is a little bit more difficult. So here, we're going to look for the limit as x approaches 5/3 of the square root of 2x squared plus 1 divided by 3x minus 5. So again, just to verify, we know it's a vertical asymptote because if it was horizontal, we would have been looking as x approached infinity or negative infinity. So here we're assuming this is the vertical asymptote, and the only other thing that a factor on the bottom of a fraction could possibly be is a whole. And the only way it's going to be a whole is if you can see that exact same factor on the top and you can cancel them. And that is not the case here. There is no 3x minus 5 anywhere on the top, nor could there be. And so I'm going to say this does not exist as a limit, and it's unbound. And that means that we have a vertical asymptote at x equals 5/3. So now we'll go ahead and look for the horizontal asymptotes for the same function. So I'm going to look as x approaches negative infinity and as x approaches positive infinity. And first I'm going to consider, I have to consider what the degree of this function is. So if you look at this, I've got a square root and I've got an x squared. So that means the degree of the numerator is 1. So you guys can see that I've got a square root, but I've got an x squared. So that means the degree of my numerator is 1. The degree of my denominator is 1. So that means that for this problem, I am just looking at the coefficients of this problem, basically. That those are the numbers that they're going to be. I know that the number that I'm plugging in for infinity on the top and the bottom are going to be the same size. They're going to end up canceling each other out. All right? So when I consider what happens when I plug in negative infinity, I've got negative infinity squared, so that means that this number is going to stay positive here. But on the bottom, when I plug negative infinity in for this x, that's going to make this this denominator a negative number. All right? So when I plug negative infinity on the top, it's going to stay positive. But when I plug it in on the bottom, it's going to make this negative. All right? So now I have to consider, if I think about the square root of the x squared, that means that this is just a plain old x. And so these two are going to be the same size when I plug in infinity. So that means that now I'm just going to be looking at this part right here. And so then root 2 over 3 is what would be left over there. So I can see that on the left side of my graph, the curve would be approaching an asymptote, a horizontal asymptote of root 2 over 3, negative root 2 over 3. All right? Now I'm going to do the same thing for the function, but I'm looking at the right side of the graph this time. And on the top, when I plug in infinity, I just get a positive number. When I plug in infinity on the bottom, again, I get a positive number because those are positives. The square root of x squared means that these two are going to be the same size of large number, and so I can think of them as canceling out. And that leaves me with root 2 over 3. So it looks like I have two horizontal asymptotes here. I have negative root 2 over 3 on the left. That's what the curve is approaching on the left. On the right, you have a different horizontal asymptote that the curve is approaching. So it looks like we've got two of them there.